So, so we're going to start with the first exercise if you have the access to the files and you have things working. So this is a very simple exercise. We're basically going to just run an alanine dipeptide in water just to make sure that you have everything working properly and to introduce you to a typical OpenMM script in Python. And I think Peter already went through the script, but I'll just go through once again just to, get you an idea about these are the exact set of lines that you have to use for writing the scripts later on in this session. So this basically you're importing some files from Python. So you have to always use these. So include these definitely. So the second set of lines is basically that you are providing a PDB file in this instance, and then you are providing which are the exact force field files we are going to use for running this simulation. So in this case, I have Ember99SB as my force field for protein, and I have tip3p water for my explicit water model. Similarly, if you have other force fields, we have all the Ember variants included. Ember 03, Ember 99SB, ILDN, and all other forms are included already in the OpenMM. So you have to provide the names of these XML files whenever you want to change your force field. So if you want to, or if you want to use an implicit solvent water model, you'll have to change the force fields here. So so whenever I ask you to change a force field, you have to change these files. The other thing is that this set of lines are actually sort of providing you the basic set of parameters for running your simulations. So for example, here we're providing the PDB as a structure. We are going to use PME. This is explicit. The non-bonded cutoff, you can change it to 1 or 1.2 or something around that. Constrained hydrogen bonds basically implies that all the OH bonds are constrained so that we can use a larger time step of 2 femtosecond or so. And here we are specifying the integrator. So in this case, as Peter told you, that we are using the Langevin integrator. And this is your temperature, friction coefficient, and the time step. But there are other integrators available in OpenMM as well. And in this case, Langevin integrator implies that you're using Langevin thermostat as well. So this is like an NVT simulation. And you can include other thermostats and other integrators, and I'll go through that later on. But this is the line, for example, is specifying your integrator here. And then when you create this context so that you have all the information that you need to run your simulation, and you create this simulation object. And then you give your starting positions for a system, and then you can minimize this step. So you can either do, when you're minimizing your simulations, you can do maximum iteration, or you can also provide tolerance for the minimum energy change. This is another set of lines where you want to see what your simulation is doing, whether it is running properly or not. And you can provide, this line basically is telling you that give my output into this PDB format. You can have a DCD format as well. And this line at the end basically is telling you that print out the step number, potential energy, and the temperature of the system at an interval of 100. So you have a variety of reporters. You can report volume, density, and I'll go through that later. And then you basically run your simulation as a number of steps. So this is the basic construction of a script. You can just write and copy these lines whenever you're writing a new script or running a new system, and you can make appropriate changes in this file. Okay. So it's important that you understand this basic file. So we want you to run this exercise and see if everything is working for you. As I said, this is also a test for your OpenMM installation, just to see whether you're able to get proper results after running this. For the next exercises, I'll just go through some basic things regarding running simulations, some of the options that you have in your scripts, and I'll just go through them one by one. And then we'll do another exercise where we'll try to simulate a protein in water. So as I told you that you are specifying the water model that you're using in this force field command, where you're saying that tip3p is your water model. But you can have a variety of water models. which are built into OpenMM. So you have an explicit water model, or you could have an implicit water model. So in explicit water model, you have the water is represented by atoms, and you have direct. Your energy function is basically the protein forces the energy to water, and then protein-water interaction. But in the implicit solvent model, you have basically a mean field where the entire effect of the water and its interaction with itself and the protein is accounted by some sort of a solvation-free energy term. And so basically, the implicit solvent models are important in the sense that you could do a much longer simulation with the implicit solvent models, because you're not really calculating the forces on all the atoms in explicit water model. So just to give you a very brief introduction of what this actually is that so water is like moving much more faster time scales, diffusion time scales, as compared to the motion of the protein. So you can represent it as I said, as a mean field or a continuum, and then you can take the effect of the water in the entire solvation term. So for each atom in your protein, you'll have a term that will take into account the solvation-free energy. So you can think of it in terms of two components. One will be the electronic component. So you have charges on the protein surface, and they're going to affect the interaction with the water, and so you have to account for that. And the other thing is the non-polar component. So basically, the effect of creating a surface equivalent to a protein in the water. So obviously there is a surface tension effect, and you can account that by using a very simple surface tension into the surface area of the protein. So this is the simplest of the water models that you can think of, and to calculate this electronic component, what has been done is there is an approximation called generalized Bond. I'll not go into great detail, but the basic idea is that you have this protein which are much lower dielectric constant as compared to the water medium, and you can have the effect of the charges embedded onto the protein surface and water. The only thing you have to specify in these equations are the radius terms, and you can fit those radius and have the effect of the implicit solvent model. So all these things have been done by others, and what has been done is these models have been included into the OpenMM. So for the explicit water models, again, you have a variety of choices if you want to run an explicit simulation. 3P is basically the 3-site water model, but you can also have the 4PEW or TIF5P. And the SPCE, which is like the standard water model with the GROMACS. If you want to do an implicit solvent model, you have the choice of using the GBSA OBC solvent model. And these are the names of the files. So if every time you're changing a force field, you'll have to use these names in your force field files. So you have to be careful with it. And this is the name of the file for running the implicit solvent model, the OBC. And the last one is the implicit solvent model that you want to use with amoeba force field. So these were the force fields, but then you also have a choice of a variety of integrators in OpenMM. So what we have shown in the first script was the Langevin integrator. So you specify your temperature, you specify your friction coefficient, which for explicit would be just 1 picosecond, and the time step, which is 2 femtosecond in this case. But if you want to do a constant energy simulations, you may want to use a Verlet integrator. And in the Verlet integrator, you don't really specify the temperature. The only thing you're specifying here is the time step, because there's no friction term there, so you also don't specify the friction coefficient. If you want to do Brownian Dynamics, again, I'll not go into details of what Brownian Dynamics is, but if you want to do it, you'll have to. It is built in. For some cases where you really don't know what is the time step you're going to use for your system. So, for example, if you're minimizing your system, you want to use a much smaller time step. We also have the variable time step integrators. So these are basically same as the earlier integrators. So you have a variable Langevin integrator. So instead of specifying the time step, now we are specifying what is the tolerance of the integration. So once you're integrating these equations of motions, what is the tolerance that you need to have? And it will automatically adjust the time step based on the tolerance. If you want to use a constant temperature simulation with the Worley integrator, you'll have to include these thermostats. So you have an option of using an Anderson thermostat. And if you want to do a constant pressure, you can also use a Monte Carlo barostat with these integrators. So these were some of the choices that you have in terms of integrators for temperature baths, for pressure coupling in OpenMM. And then if you go to the system command here, you see this term called constraints. So by constraints, there are a variety of constraints that we are using here. You could have default where you have no constraints. So then you'll have to go to a smaller time step, like 0.5 or 1 femtoseconds. But if you want to constrain all the bonds of the water, for example, or hydrogen atoms, then you can use an edge bond constraints. Or you can constrain all the bonds in the system with this term. And then H angles is even going further, where you're basically assuming that there's no movement of the hydrogens, HOH angle. So you can go to an even higher time step with these constraints. There's another option which I have not listed here, is that you could have rigid water in OpenMM. So you can say rigid waters is true, and then you can have a water as a single rigid molecule.
Rigid water is true by default.
Yeah, rigid water is true by default. So every time if you don't specify a constraint term, you'll have rigid waters. You have to say constraint equal to none
No, but even if you do that, it will still make water.
Okay.
Unless you say rigid water equals.
It's false. Okay. So that basically brings us to the second exercise, and the purpose of this exercise is that you have a given PDB file, and you want to run a simulation of this protein in an implicit solvent. So the protein that we are using as a test case is Villain. It's a very tiny 35 residue protein, and I've taken the PDB file from the PDB database, and that's provided to you as an input in your folder. So what I want you to do is to copy the exercise 1 to exercise 2, and try changing the input files, the force fields, and try to run this simulation and see what are you getting. Now, I'm just telling them that if you're using the force field files, you need an Ember force field file for the protein and an implicit solvent file for the OBC. So you'll need 2. So you have to replace the tip3p with your implicit solvent, and which is usually the case when you download a PDB file from an PDB database. Most of the time it is missing some atoms, and usually if you have X-ray diffraction, it's missing all the hydrogen atoms. If you have NMR, you have hydrogen atoms, but it could still be missing some atoms. So you can take care of these issues by using the modular class in OpenMM. So typically the PDB file that you get would have, from I said X-ray diffraction file, would have most of the heavy atoms, but you will still be missing hydrogen. If you want to do an explicit water box around your protein, you have to build that water box. So usually people use a variety of tools to build these water boxes. You can do this in BMD. You can do this using Ember tools and stuff. So there are some basic functionalities that are already built into this new class in OpenMM, where you can add the missing atoms, missing hydrogens, solvate it, add ions to your system to make it neutral. So the idea is that the change that you need to make in your input file is that you have to define this, you have to create this object for a modular class. The input that this class is taking is your PDB topology and PDB positions, so that it knows what is the initial number of atoms that you have and what are the atoms that you're exactly missing in your template. And once you have created this object, you can call in some functions in the modular class to build the missing atoms or to solvate your system. And then for all the steps after that, they will be exactly the same. The only thing you have to be careful about is that now your PDB is now no longer has the exact or the list of the complete number of atoms. Now that you have modified your list, your topology and your positions, because the number of atoms have changed, so the connections between them have changed, the positions of those atoms are not complete. So you have to use modular.topology and modular.positions from the remaining part of your script. So the functions that you could use are basically for adding hydrogens. which would be the function that you would have to use in this case. If you look at your protein input file in VMD, you will see that it does not have hydrogen atoms. It's missing most of the hydrogens. So you can do modular.add hydrogen, and you can specify which force field you have to use, because different force fields will have different names for the atoms. So for Ember, earlier versions of Embers could have a different name for some atoms in the amino acids, but the new force field may have different names. Similarly, you can also specify the pH at which you want to add your hydrogens. And that's an interesting feature, because based on the pH, the charges on the side chains are going to change. So if you have a pH of 9 or 10, which is very high pH, you'll have everything will not have a hydrogen. Whereas if you're at a very low pH, like 1 or 2, you'll have to put a hydrogen on most of the amino acids. So you can specify what pH you would like to use, and then based on that, it can put in the hydrogens, it can build in the missing atoms. If you want to add solvent, you can basically say modular.add solvent. Again, you provide the force field file. What is the model of the water that you want to use? And as I already told you, the models were like TIP3P, 4P, EW, 5P, and SPC. If it is explicit. The other thing that you can do with add solvent is that you can either specify the box size that you want. So you can say that put my protein with explicit water molecules in this fixed box size. Or you can say that I want a water layer of 20 angstrom or 10 angstroms from the protein surface. And you can build the box based on that. So these are the commands that you will probably use for building the solvent. Now, if you want to add ions as well, when you are building your system, you could use, again, add solvent. Ionic strength is basically the concentration of the ions that you want. So the default ion in the OpenMM modular class is sodium chloride. But if you want another atom like potassium or cesium or calcium, or if you want another negative ion to solvate your system, you can specify these names. And you can look at the application guide, section 4, and that has all the details of the class and the functions that you're using. So for this exercise, what we want to do now is that we want to use the modular class and build the missing atoms, and then do this implicit solvent simulation. I think we have been able to add the hydrogens here. So I think most of you have been able to do it. The only thing you have to create this modular object, and then you have to do modular.add hydrogens and provide it the force field. The one thing that everybody is sort of making a slight mistake on is that you have to provide 2 force field files. And the difference here is that this force field file is for the protein parameters, so angle, bond, hydrolysis, not bonded, everything is here. And this file basically contains only the implicit solvent parameters for the atoms in the Ember 99 SP or Ember 99 force field. Okay? So every time you have to do implicit solvent model, you have to provide this file instead of tip3p.xml in the exercise 1. Okay? So you have to provide 2 files. That is something that everybody's making a mistake on. The other thing was, I think all of you have done this right. So now what you're going to do is that we are going to do explicit solvent. So you have to use now add solvent command and play with it. So so you have to just take the exercise 2.py or py, or you can start from exercise 1, whatever. And now you have to do explicit solvent. So there will be a lot of things that you have to put in back from exercise 1. Like you have to put back PME, and you have to add missing water molecules, the whatever box you want to create. So I think you should use modular.add solvent for this. And let me know if you are having issues with this. So I think most of you got it working. So now I can just show you what was the answer. You have to specify. I think the mistake that most of the people are making is, again, that you have to specify tip3p here as your force field if you are giving the model as tip3p. If you're giving model as tip5p, you have to give the force field here for tip5p. You have to give some padding. And if you're not giving either padding or the box vector, what it does is it just takes the dimensions of your existing system and tries to fill in water there. And if your PDB does not have the crest command at the top, which tells it what is the box size, then it doesn't really know what box is supposed to put the water in. So you have to always just specify the padding or the box size to solve it. And I think other than that, everybody was able to get this done. I think that was sort of the end of it. So the goal is I think this entire exercise, the goal was that you are familiar with editing the Python scripts. You have basic ideas about what you're supposed to do to run a simple simulation. And it will be very useful for the breakout sessions where we are going to work on specific problems which will be a little more involved in the afternoon. So yeah, I think that's good.